Power and power losses case of DC machines. This is total power flow diagram in case of DC machines, including iron losses and copper losses. So we can use same machine as generator and motor also. So one is generator mode, second one is motoring mode. Under generator mode, power is delivered to the load. Under generating mode, power is delivered. Under motoring mode, power is absorbed. So in case of generator, the armature is driven by external prime mover. So that power is considered as shaft power, power in, and here the direction of rotations. Generator rotates in clockwise direction, and the directions of two torques. One is developed torque and counter torque. These two torques are opposite to each other. So basically we are dealing with power flow. So this is the power input from the external prime mover, and there will be few losses at this armature rotation. Those are brush and bearing losses, air friction losses. All this comes under frictional losses, rotational frictional losses. And there will be few iron losses and hysteresis losses in the armature circuit. The armature is made with silicon steel laminations, so there will be some hysteresis and eddy current losses in this armature. So after subtracting these frictional windage losses and this iron losses in the armature circuit, the remaining power will be mechanical power. So here power input is input power from the external prime mover, and the losses are friction and windage losses and hysteresis eddy current losses in the silicon steel laminations of armature. So the rest of the power is mechanical power. So this power is considered as mechanical power or electrical power, which is E into I. The voltage developed in the armature circuit and current in the armature circuit, E and I. So this is electrical power. So this side, this is electrical part. This side, this is mechanical part. So at this junction, both mechanical power equivalent to electrical power. And these are the losses in the electrical circuit. Copper losses, the shunt field winding, copper losses, armature winding, copper losses at brushes. All these losses are ohmic losses. So the field winding, it can be shunt field winding and series field winding. These field winding losses are directly dependent upon square of the current. And drop across brush, we generally take it as voltage drop. So voltage drop across brushes is approximately 1 volt per brush. But we can also consider this brush voltage drop as ohmic drop. So the type of losses in the electrical parts will be field winding losses, armature circuit losses, and brush voltage drop. After subtracting these losses from this electrical power, the rest of the power is output power, which is equivalent to terminal voltage into load current. The total power equations can be divided into two parts. One is mechanical part, second one is electrical part. On mechanical side, the total power input is power input from the external prime mover, and the total losses we have to subtract. The losses will be rotational losses and iron losses. After that, the rest of the power is mechanical power. And from electrical part, total electrical power is equals to losses. Losses are equals to field copper losses, armature copper losses, and brush drops. After that, the rest of the power is output power, terminal voltage into load current. So in this case, the mechanical power is equal to electrical power. So this is in case of generator. In case of motoring mode, the total losses and everything is same, but only the direction is different. So in case of generator, the direction was in this direction. In case of motor, the direction will be just reversed. The direction will be in this direction. So in case of generator, that was shaft input power and terminal output power. In case of motor, terminal input power and shaft output power. Rest of all the terms will be same. Electrical side, copper losses, field winding copper loss, armature winding copper loss, brush drops, all this will be electrical side losses, and electrical power is equivalent to mechanical power in the case of armature. And from mechanical power, iron losses, friction and windage losses, all these losses will have to be subtracted. After that, rest of the power is only shaft power. And the power relation is just in opposite direction. The rest of all will be same. So efficiency in case of generator and in case of motor can be divided into two parts. One is mechanical part, second one is electrical part in both the cases. First we have to consider mechanical part in case of generator, second we have to consider electrical part. Then finally we get output. So this is input, that is output. In case of motor, first we have to consider electrical part, second we have to consider mechanical part. This is input and this will be output. So efficiency in terms of mechanical, the output power that is Eg by Ia, the input power that is power from the shaft. In terms of electrical, the output power terminal voltage into load current divided by input power Eg into Ia. You multiply these two, here numerator, here denominator, both will get cancelled, and the final efficiency will be terminal voltage into load current divided by input power from the prime mover. So this is total generator efficiency. Similarly, in case of motors, this is efficiency of electrical part, this is efficiency of mechanical part, numerator, denominator get cancelled. Total efficiency of motor is output power, that is shaft power divided by input power, that is supply voltage and load current. You can consider general efficiency equation, output by output plus total losses. This is general equation. In this case, these are total copper losses, total iron losses, and condition for maximum efficiency. That is when constant losses are equals to variable losses, that is equals to iron losses equals to copper losses, then maximum efficiency can be obtained. Copper losses, I square R losses equals to iron losses, Pi, and the efficiency is only 50%.